Başlayalım mı?
Başladı.
Okay. So. The algebras, mainly semi-simple the algebras. Bir özet yapacağım yaptıklarımızın. Abstract of the past weeks. Bir defa her şeyden önce cisim cebirsel kapalı olacak ve karakteristik olacak. Mainly K is algebraically closed of characteristic zero. Bazı sonuçlar başka cisimlerde içinde geçerli olacak. Ama bunu şey yapıyoruz. So what's Lie algebra? Lie algebra is first of all a vector space over a field K together with a bilinear alternating product called bracket operation. With the Jacobi identity, değil mi? So it is not associative, but it is there is some relation between products of x, y, and z with the Jacobi identity. It says x, y, z, and then you cyclically change it y, z, x plus z, x, y is equal to 0. Okay, examples. Example one, take any algebra, any algebra, not commutative. If it's commutative, it's trivial, and define xy to be xy minus yx. Example two, any algebra. Look at the derivations of A. Instead of delta from A into A, linear, such that delta of xy is delta x times y plus x times delta y. And under the operation, delta 1, delta 2 is equal to delta 1 composed with delta 2 minus delta 2 composed with delta 1. This is also the derivation. Example 3, GLV. This is the endomorphisms of V over K. But you don't see it as a this is a ring. In fact, it's an algebra over K. But you don't see it as a ring. You take together with forget multiplication, forget composition, and instead take bracket operation. Phi PC is equal to, like this one, phi composite PC minus PC composite phi. And you have, of course, subalgebras of these. These are called linear Lie algebras. Example 4, you have SLV, the endomorphisms, elements of GLK of V because trace is 0. Yeah. This is the algebra. In fact, all these commutators are in here. For any free MPC here, the commutators are in here because trace of this is equal to trace of this. Yeah. And you have a map from here to into GLV into SLV. That takes phi or A. You can see them as matrices if you want to. View as matrices and go to XA. This is the usual sum of A to the N over N factorial. These have trace of determinant of XA is e to the trace A. So that if trace A is 0, then this is 1. And we have seen other classical algebras, like three others, orthogonal, symplectic, and so on. Okay. What else? We have seen ideals, right? Ideals, quotients, homomorphisms, and the fundamental theorems and so on. Everything is valid. Her şey geçerli burada da. What's the representation? Of a Lie algebra. Is a Lie algebra L is a Lie algebra homomorphism. From L into some GLV. So you represent it as linear, as a linear Lie algebra. Well, it may not be faithful. You know, this may not be one-to-one. Okay? You may lose some knowledge here. Okay, and we have a usual one, the adjoint representation. This is from L into GLL. That takes an X here. It's sent to add X. What's add X? Add X is a linear map from L into L. It takes Y. Add X, Y. This is what we expect. This is the bracket of X and Y. Okay. And so we have here add of X bracket Y is equal to add X bracket add Y. So it's a Lie algebra homomorphism. The kernel of add X is of course the center, clearly. When this is 0, this is 0, if and only if this is always 0 for any Y, it means the X commutes with Y. So the kernel of add is equal to center of L. So L over the center embeds inside GLL. It's always linear. You divide by the center, you get something linear. What's nice about linearity, here we have only bracket operation, and here we have also, this is endomorphisms, we have also a composition, right here, this switcher. Okay. Well, okay, so we have seen some automorphisms and let me see. Automorphisms. You know what automorphism is, of course. It's a Lie algebra isomorphism from Lie algebra into itself. It's a group. Suppose that L is linear, so it's inside GLV. So if you have, for example, if G is invertible and GL is inside L, this means that GL is equal to L, since L is finite dimensional, G is invertible, so GL must be equal to L. Then the conjugation by G is a Lie algebra automorphism, clearly, because it's linear, right? Yeah, G inverse bracket xy. G, you can put this inside. This is xy minus yx. So it's linear, so it distributes, and then you can put here and here G and G inverse. All right. Now, something else. Now, suppose X is in L. So this is second case. If X is adnilpotent. Adnilpotent means that ad X is nilpotent. Ad X to some power is 0. You can see there's ad X is something upper triangular. Here's nilpotent. Then X ad X makes sense, but it goes only this equal to 1 plus ad X over 1 factorial plus ad X square. By square, I mean composition, of course. 2 factorial plus. And it tends to stop somewhere because it's adnilpotent. Say it stops at K. At K minus 1. Of course, here you need characteristic 0, or at least characteristic greater than or equal to K. Now, this is automorphism of L. More generally, take let delta be a derivation of L. Here in the definition of derivation, there is derivation. And not necessarily associative. Yani licebir olabilir. Okay. So this means that delta of xy is equal to delta xy plus x delta y. So it means delta is linear and it has this property. If delta is a derivation, it must be nilpotent. Evet. Suppose it's nilpotent. It means that if you compose it enough times, find many times, you get 0. Then exp delta exp exp delta is equal to identity plus delta over 1 factorial plus delta of the k minus 1 over k minus 1 factorial is automorphism. Okay. We have seen this. Right? Okay. Such an automorphism is called inner automorphism. Inner automorphisms is a normal subgroup. It's a normal subgroup in the automorphisms of L. Okay. Next. Then we have seen solvable and nilpotent the algebras. This is exactly like in groups, no difference. Okay. Now there's a theorem here. There's a theorem. Engel. It says that if all the elements of L are adnilpotent, then L is nilpotent. You see, what does it mean that L is nilpotent? What does it mean? It means that if you bracket enough times, you get to 0, right? So if you bracket x1 bracket, x2 bracket, x3 bracket, and so on. So if you do this enough times, you get 0. In particular, if you do x with itself enough times, you get 0, so add x. Okay? So this implies that every element is adnilpotent. And if every element is adnilpotent, then L is nilpotent. And to put this, we use the lemma. It says that x in GLV is nilpotent, then x is adnilpotent. Adx is nilpotent. That's what we used. And we put actually a better theorem than this one, another theorem, nothing better maybe. Theorem. L, a subalgebra of GLV, definite dimension, of course. L consists of nilpotent endomorphisms. And V is different from 0. Then there is a V in V non-zero. Such that L of V is equal to 0. So it means that elements of L have a common eigenvector V. Eigenvalue must be 0, of course. It's important. So. Corollary. Under the hypothesis of the above theorem, so you can choose a basis of V such that elements of L are upper triangular, strict upper triangular. Of the theorem, we may choose a basis of L, for which L embeds in L inside. Choose the basis. N K. There's an N and V. And nasıl yazıyor? And F. And then comma, we call K. This is strict upper triangle matrices. Huh? In other words, there's a flag. So the elements of L decrease the flag. Right, of course. It says there's a lemma here, but I don't write it. If L is nilpotent, then any non-zero ideal intersects the center, like in the groups. Okay, now chapter 2, semi-simple algebras. What does semi-simple means? It means its solvable radical is zero. So what solvable radical is the maximal solvable ideal. Radical of L is the, of course there is one because sum of two solvable ideals is a solvable ideal. İki tane idealin toplamı idealdir. If they are solvable, the sum is also solvable. Is maximal solvable ideal of L. Yeah. Of course, radical of L over radical of L is zero. So you killed all the solvable ideals. There's nothing left, right? L is called semi-simple if and only if radical of L is zero. Okay. This means that L is rich enough, and there's no there's nothing simple inside. Okay. It's interesting enough. Theorem. Lee, obviously also Colchin maybe. Lee Colchin. L inside GLV solvable the algebra. Then there's a common eigenvector. And V is different from zero. Then L is a common eigenvector. This means that you can upper triangularize it. So, corollary, L can be solvable linear Lie algebras can be upper triangularizable. Right? There's a basis of L of V under which L can be embedded inside upper triangular matrices. Okay. Next we have Jordan Chevalier decomposition. call X an endomorphism of V semi-simple, if it is diagonalizable. If the root of its minimal polynomial are distinct. For example, this is not semi-simple because its minimal polynomial is x minus 1 square, and it has two roots. Minimal polynomial is x minus 1 square. But this is x minus a. X minus a is equal to 0. And this is x minus, what is it? X minus a times x minus b? Right? So if a is different from b. Okay, and this means this is the same as, since K is algebraically closed, this is the same as saying that X is diagonalizable. Okay. Otherwise, if K is not algebraically closed, X will be diagonalizable in an extension of K. If X is semi-simple, W inside V, and X of W is inside W, then you can extend X to W, it is still semi-simple. Right. Proposition. X endomorphism of V. You see, when you see endomorphism of V as an algebra, as a normal algebra, as associative algebra, you write like this. If you see it as a Lie group, then you write like this. So what do we have? A, there exists XS, and there exists unique XS and XU. XN or XU, I can't say. It's XN. It's semi-simple, and it's important, such that X is equal to XS plus XN, and XS and XN commute with each other. So they also commute with X. Yeah.
With constant term 0. With constant term 0.
What constant term? There's nothing. I didn't say it. And further, there's a polynomial. There are polynomials P and Q over K without constant terms. Such that XS is equal to P of X and XN is equal to P of X. This means that hence, if X of W is inside W, then XS of W is also inside W, and xn of W is also inside W. So in other words, if you have the composition of X is endomorphism of V, and if you restrict it to W, suppose X times W to W, then you have also the same decomposition. Right. So this is called, there's only one. This is called semi-simple part of X, and the other one called nilpotent part. Okay, so if we have, and also add X. So add X also has a, also, of course, we have, this is clear, right? Since we have the sum here, this is equal to this. This is, of course, inside endomorphisms of L. But furthermore, this is semi-simple. This is equal to adx S, and this is equal to adx N. Okay?
Ben şeyi konuşmuştum. X endomorfismadan aldık. Ondan sonra Adex yazdık.
So this is, this is X bracket Y, adx of Y. Here it is.
Bunu anladım. Sadece abstrakt bir cebir olmamış gibi.
No. L is a linear, and X is endomorphism of V. And, sorry. So L, yes. No, it's fine. It's fine. This is inside endomorphism. What do I mean by XS? So X is endomorphism, of course. X is endomorphism of V. Okay, so XS exists. So I shouldn't say endomorphism L here. I should say endomorphisms of endomorphisms for K of V. There's another lemma. Let A be a finite dimensional K algebra, then derivations of A. So derivation of A is a Lie algebra, right? This is inside, of course, GLA, right? They are linear. Derivations of A, where is it? This is inside GLA, right? And it is a Lie algebra under the bracket operation. So if you take an X here, as endomorphism of A, it has a semi-simple part and linear part, and nilpotent part. They are both in here. Then the division of A contains, then the elements, okay, and the division of A contains the semi-simple and nilpotent part of its elements. In other words, if delta is a derivation, delta S and delta N, they are both derivations. Okay, now we have the famous Cartan's criterion. Lemma A inside B two subspaces of GLV, subspaces. So I should say here, maybe K here. Subspaces, dimension infinite. M is equal to set of X in GLV such that XB is inside A. So adjoint X takes B inside A. Okay. So you can repeat this again. You can take adjoint X again. Suppose and X is in M. Then if trace of XY is equal to 0, all Y in M, then X is important. Okay, maybe I should have written this lemma. This is technical lemma. Using this, we prove Cartan's criterion theorem. L subalgebra of GLV, different dimensional, and trace of L prime L is equal to 0. So L prime is the L commutator L. Okay. If this is equal to 0, so it means you multiply them. You can multiply here in GLV. Okay. It's equal to 0, then L is solvable. Then L is solvable. Corollary. Let L be Lie algebra. So this is the nonlinear version of this, be a Lie algebra, such that. So I want to use this. So I for X in L, I use adjoint X. If then such that trace of add X add Y is equal to 0, all X in L prime and Y in L, then L is solvable. Okay. Next, we have the killing form. Okay. Killing form, complete divisibility, representations of SL2. We have to get right in this. And the roots, space decomposition, orthogonality properties, integrity properties. And we arrived until the end almost. There was one place where we were stuck. It was clear. In fact, it was very easy because we didn't understand well enough the representations of SL2. Okay. So I will continue this later. We fill the black box. Now, cut the şey keselim.